So if we look at probability, you've got a random variable x, so the x could be a length of a manufacturing process or something, and you take a bunch of, in the case of manufacturing, you've got n number of widgets that you're making that has this variability x. The probability that a chosen value of that dimension or whatever in the manufacturing process is smaller than a certain limit, I guess, which is given by x with that squiggly line underneath. The probability of that is you take the number of widgets or whatever that has this case, and you divide them by the total, and that gives you the probability. So say I'm making 10 widgets, okay, and there's a certain dimension that has a random component to it, and I'm looking for the dimension where that is less than, say, 5 millimeters or whatever. Then I look at all the parts that have that dimension of less than 5, and I divide them by the total number of parts. So my probability of getting, my widgets will be that number divided by the total number of widgets I've made. Okay, that makes sense. Yeah, if you're making 10 things and you're looking for the ones where the dimension is less than, say, 5 millimeters, and there are 5 of them, then obviously 5 over 10 gives you 1/2. So the probability of getting this being the case is 0.5. Okay, makes sense. Straightforward. P, which is known as the probability distribution function, it's the same thing, but as n approaches infinity. Okay, so you get the same sort of process. And like I said, as n approaches infinity, you're reaching this limit condition. And obviously, if big P is a half still, then obviously that's I know that half the time I'm going to get a part that meets that limit that I've set. Now, if we take the derivative of P, okay, with respect to x, this is known as the probability density function, the PDF, okay? And you'll come across this time and time again as you do engineering, but yeah, PDF, probability density function, that's denoted by little p, okay? And so, obviously, if little p is the derivative of p to the x, the big P, okay, then you can take the integral of p and little p and you'll get big P, yeah? And the integral is important because that gives you the area underneath a curve. And we know that the integral of little p dx, this always equals 1, okay? Because essentially what we've got with this function is you've got a curve that represents all the possibilities in terms of some random vibration, okay, underneath a curve. And the integral from minus infinity to positive will always be 1, okay? So if your curve looks, I don't know, like some sort of bell-shaped curve or whatever, then every value, every possible variation in that thing that you're looking at, the x, that dimension or that variation or whatever, will always occur within that, underneath that curve. And so here's a particular example. We have what's known as a normal distribution, but essentially what we've got is in this case we've got a number of samples, okay, and number of occurrences. So specific values or whatever you take. You take this example. We know that this is going to be quite frequently. I'm going to have this this value of this sample. Okay, so this could be my x term or whatever. And so I've got 8,000 of them, whereas down here I've got very few of them, and I've got 256,000 samples in a sense. Okay, so this could be my so like I said, a manufacturing process. My nominal value, the thing I set my dimension to, is 130 millimeters or whatever. But because of the manufacturing process, there's going to be some variability in meeting that target, and the distribution I get looks like this. So for 256,000 points, I could draw a histogram. So I measure each one of those, and I get a distribution. Now the PDF of that obviously looks something like this, okay? And so that's my distribution. And so the area underneath this curve, okay, is equal to 1. Because the chance of me having a part that's within this sample, within this distribution, is 100%. Anything that I make will be underneath that curve. Okay, so that equals 1. The area underneath that curve equals 1.